The title of the topic is Influence of Matrix Modification on Interlaminar Fracture Toughness of Glass Epoxy Laminates using Nano and Micro Fillers. Below you can find the list of authors who have contributed in this particular work. Introduction. In a variety of industries including automotive, aerospace, marine, and even civil engineering applications, fiber-reinforced polymer composites have drawn attention for their exceptional qualities, including mechanical properties, impact resistance, design flexibility, and lightweight nature. Fiber-reinforced polymer is a composite material which is made up of a polymer matrix reinforced with fibers. Hybrid composites are referred to as high-performance fiber-reinforced polymer materials used in safety-critical structural applications. However, the true thickness properties of the composites like delamination resistance are very poor as compared to other directions. This is due to the poor performance of the matrix phase in the interlaminar region. The most common method for enhancing interlaminar fracture toughness is to modify the resin system using different fillers like graphene, carbon nanotubes, multi-walled carbon nanotubes, ETBN, epoxy terminated butadiene nitrile, silicon carbide, graphene nanoplates, and carbon blacks, etc. Many researchers have concluded that the attributes of optimum weight percentage of reinforcements, length, aspect ratio, and orientation of fiber reinforcements and/or fillers will play a significant role in enhancing fracture toughness. Otherwise, agglomeration of particles will lead to the development of the microcracks in the resin phase, which is the cause of reduced fracture toughness in the interface region of the composites. Fiber bridging is the key aspect in slowing down the rate of random propagation of crack. This investigation aims to assess the effect of micro and nano filler, that is aluminum oxide, sodium carbonate, and multi-walled carbon nanotubes on mode 1 and mode 2 fracture toughness of glass epoxy composites. The incorporation and proper dispersion of fillers in epoxy resin were achieved with a magnetic stirrer. The hand layup technique was adopted to manufacture the composite laminates. The mode 1 and mode 2 tests were performed as per ASTM D5528 standard and ASTM D7905 standard respectively. The SEM examination was used to describe the fiber matrix interface and failure mechanisms. The unidirectional glass fiber with modified epoxy composites is manufactured using hand layup technique for mode 1 and mode 2 tests. The required thickness of the composite laminates is attained by maintaining an equal number of unidirectional glass fibers at the top and bottom of the pre-crack. The pre-crack is achieved by using a separation film of 14 micron thickness at the midplane of the laminates. The unidirectional glass fibers are laid one over the other and modified epoxy resin is coated and dead weight is placed on the composite and it is cured. The curing of composite laminates is done at the room temperature. Now this is the methodology which is adopted in order to carry out mode 1 fracture test, which is done according to the ASTM D5528 standard, and the other figure shows the methodology which is adopted in order to carry out the mode 2 fracture toughness, which is carried out by using the ASTM D7905 standard. Mode 1 fracture test is carried out using double cantilever beam specimen, whereas mode 2 fracture test is carried out by using ENF specimen. Lastly, conclusions. The matrix modification was done effectively by adding nanofillers like multi-walled carbon nanotubes and microfillers like aluminum oxide and sodium carbonate to the epoxy matrix. The modified epoxy matrices were used to make the composites comprised of unidirectional glass fiber reinforcements. The addition of these fillers in the epoxy matrix was found to be effective in increasing the out-of-plane load-bearing capacity of the composites as compared to plain glass epoxy composites. Also, the fracture toughness enhanced in the range of 20 to 26% and 14 to 17.5% under mode 1 and mode 2 loading respectively after the addition of fillers. The 1 weight percentage of multi-walled carbon nanotubes filler seems to be the optimum concentration to get enhanced fracture toughness values. Further, increasing the concentration of multi-walled carbon nanotubes showed no significant improvement in fracture toughness values. Now for 0.5 weight percentage of aluminum oxide, which is Al2O3 microfiller concentration in epoxy matrix, gave promising prospects in attaining the higher load carrying capacity of the composites. The fracture toughness values under mode 1 and mode 2 loading were increased significantly by 20% and 7% respectively in composites composed of epoxy matrix, which was modified with 0.5 weight percentage of Al2O3, that is aluminum oxide. The filler sodium carbonate, that is Na2CO3, added in epoxy glass fiber composites was also favorable in increasing the composites out of load bearing capacities. The optimal concentration of 1 weight percent Na2CO3 in glass fiber epoxy composite is found to have higher load bearing capability as compared to the other concentrations such as 0.5 weight percent and 2 weight percent addition of Na2CO3 in glass fiber epoxy composites. The composites consisting of 1 weight percent Na2CO3 in glass epoxy composites showed higher fracture toughness during crack propagation under mode 1 loading, whereas composites consisting of 2 weight percent Na2CO3 in glass epoxy composites exhibited higher toughness during crack initiation under mode 1 loading. The composites with 1 weight percentage of Na2CO3 exhibited higher load bearing capacity and higher fracture toughness values under mode 2 loading. This was the brief introduction of the work. Thank you.